Have you ever tried to build a tower out of water? Sounds completely ridiculous, right? I mean, you can easily pile up a small mountain of sand or stack stones. But if you try to do the exact same thing with water, it just slips right through your fingers and puddles on the ground. We interact with these materials every single day, but we rarely stop to think about the hidden rules governing how these different macroscopic materials behave when we actually try to hold them, build with them, or contain them.
Welcome to this explainer. Today, we're diving straight into the particulate nature of matter. And I promise you, by the end of this, you're going to look at every single object in your daily life completely differently.
So, to solve this mystery of why things behave the way they do, we have to look incredibly close. If we took a giant metaphorical magnifying glass and zoomed way, way in, right past what our human eyes can see, we'd reveal our invisible protagonists, tiny particles. Literally everything around you, the chair you're sitting on, the screen you're staring at, even the air you're breathing right this second is constructed from these microscopic building blocks. And it's entirely their behavior on this micro level that dictates the states of matter we experience on the macro level.
Now, before we start looking at specific materials, we've got to lay out the foundational rules of the game. These tiny particles, no matter what they're making up, play by three basic rules. Number one, they always have some amount of space between them. Two, they are in a state of constant motion. And three, they have forces that attract them to each other. That's it. Those three variables, spacing, motion, and attractive forces, are basically the master dials that control the entire physical universe.
Section 1. Solids, locked in place.
Okay, let's investigate our first state of matter by turning those master dials to their absolute extremes. Think about the microscopic makeup of everyday solid objects, like an iron nail or a block of wood. In a solid state, the particles are crammed together with the bare minimum space possible between them. But more importantly, the attractive forces holding them together are incredibly strong. Because of this intense microscopic grip, the particles can't really move past each other. Actually, scratch that, they do move, but they're only able to vibrate vigorously right in their fixed positions. This is exactly why solids have a definite shape and a definite volume. You can't just squish an iron nail into a new shape with your bare hands because those particles are absolutely refusing to let go of their neighbors.
Section 2. Liquids, flowing and shifting.
Now, let's see what happens when we observe a simple transfer of liquid between differently shaped containers to solve our initial mystery of flowing water. Picture this. We start with exactly 200 milliliters of water in a tall, straight glass. If we carefully pour it into a triangular conical flask and then dump that same water into a wide, flat bowl, what actually changes? Well, the volume stays exactly the same. It's still 200 milliliters, which proves liquids have a fixed volume. But the shape? It transforms completely every single time to perfectly match the bottom of its new container. This right here demonstrates that liquids have absolutely no fixed shape.
And looking under the microscopic hood reveals exactly why this adaptability happens. Compared to our rigid solids, liquid particles have slightly weaker attractive forces and a little more breathing room, a little more space between them. Because they aren't locked in that unbreakable rigid grip, these particles can slip, slide, and roll past one another. It's this increased freedom of movement that allows the liquid to flow, to be poured, and to spread out until it finally hits the walls of whatever vessel it sits in.
Section 3. Gases, total freedom.
Before we look at the mechanics here, I want to pose another quick micro-mystery to you. Imagine someone sprays a strong perfume or lights a scented candle on the complete opposite side of a large room. How does that fragrance seemingly travel through invisible, empty air to eventually reach your nose? Like, what is physically happening in the air?
Well, we can solve this by observing a process called diffusion. It's beautifully shown here with a burning incense stick. In a gaseous state, the particles are very far apart, and the attractive forces between them are incredibly weak. I mean, almost negligible. Because they aren't holding on to each other at all, these super fast-moving fragrance particles spread rapidly. They're ricocheting off air molecules until they equalize and manage to fill every single available corner of the space.
Let's actually test their physical structure. We can use a standard syringe to demonstrate just how much empty space exists between those bouncing gas particles. If you pull a syringe plunger outward so the chamber fills with air, place your thumb tightly over the open end, and then push the plunger inward, you're going to find that you can actually compress that trapped air. The volume physically decreases. No way could you do that with water. The plunger just wouldn't budge. This brilliantly illustrates that gases are highly compressible, precisely because there are vast amounts of empty space between the particles, which allows them to be physically forced much closer together.
Section 4. Summary: energy changes everything. So the crucial takeaway here is tying all these macroscopic behaviors together so we can see the whole big picture of how matter transitions, and this matrix perfectly synthesizes our investigation. Over on the left with solids, we've got minimum spacing and maximum attraction, which means zero flow. But as we move to the middle with liquids, that spacing increases slightly and attraction weakens just enough to allow flowing, and by the time we hit gases on the far right, we've reached the extremes: maximum spacing, maximum movement in all directions, and minimum attraction.
But here's the real kicker. What's super interesting about this final rule is that it reveals the ultimate driver behind the scenes: thermal energy, or heat. See, as you add thermal energy to matter, you're effectively giving the particles more kinetic energy. This added energy makes them vibrate more furiously, which increases the distance between the particles. As they push further apart, the strength of those attractive forces holding them together decreases, eventually letting the particles move totally freely. So thermal energy literally has the power to break those microscopic bonds, melting a solid into a liquid and boiling a liquid into a gas.
So just take a second and look around you right now, wherever you happen to be. Can you visualize the tightly packed, vibrating solids that make up the floor beneath your feet? Can you picture the rolling, flowing liquid particles in your water bottle? What about the rapidly bouncing, widely spaced gas particles that are constantly brushing against your skin? By understanding these hidden microscopic mechanics, we unlock a massive, deeper understanding of the macro world. But it does beg one final, pretty wild question. If just tweaking the temperature can completely alter the rules of the matter around us, what happens to these rules when things get infinitely hotter or infinitely colder? Keep applying this lens, stay curious, and thanks for exploring with me.